For the past several weeks we've been learning how to find the derivative of various functions, and we've learned quite a few skills and quite a few techniques for finding those derivatives. Over the next few weeks we'll be taking those techniques and learning how to apply them to problems to find out certain things about the function, to be able to have some idea of what the function looks like so that we can sketch it even though we may not know exactly what it looks like, and also to solve certain real-life problems. One of the first applications we're going to learn is how to find the extreme values of a function. And when we say extreme values, we're really just saying how to find the maximum and the minimum values of a function on a particular interval. Now, most functions do not have an absolute maximum, meaning an absolute highest point it ever gets, or an absolute minimum, the absolute lowest it gets, because most functions keep going forever in a particular direction, so that most of them would continue going to infinity or to negative infinity. However, we can talk about extreme values on an interval, and that's what we're really talking about here. So as you look at the definition, the working definition we have here, if C is a point on an open interval A and B, and A, B are both x values here, okay? So this is not a point, these are x values, and F is continuous on the interval from A to B, then we call F of C a maximum of F if it is greater than or equal to every other function value on that interval, and we call FC a minimum of F if C is smaller than or equal to every other value on an interval. So let's take a moment and look at what this might look like. For example, let's talk about an interval. Let's say here's our A and here's our B, and so we've got those two, and F is continuous on the interval from A to B. Now let's remember what that means. That means that once we start drawing it, we'll never pick up our pencil, and it'll continue going on and on. Something doesn't have to go in a particular pattern, but this one here, that would be our function. Okay? Now, what are we saying? The extreme values are the values that are the maximum and the minimum. So if we look here, this area right here looks like it's probably a maximum on A and B, and this area right here looks like it's probably a minimum. So we would call this point, I'm going to call it C, and then we would say that the maximum for this particular function here would be the point C, F of C. And also we could call this point here, I'm going to call it C1. C1 would be a minimum point. So it's really just a highest point and a lowest point that the function gets on the interval that we're talking about. Now, in looking at this particular function here, what if we were looking at a different interval? Suppose, for example, that we were looking at it from A to let's call this point R right here. Suppose we were looking at just the interval from A to R. Then this area up here would probably be our maximum if we're talking about just the interval from A to R. So we can take a function and look at it over any specific interval and find out if it has a maximum or if it has a minimum. Now, a theorem that you need to pay close attention to, and one of these that you're going to see again, is called the extreme value theorem. Now, the extreme value theorem says if F is continuous on a closed interval. Now, what's the difference between a closed interval and an open interval? A closed interval means that we are including A and B. Remember, up here at the top, A and B are not included in this interval. We get as close to A and B as we can, but we don't actually include them. A closed interval includes them. So we're saying if F is continuous on a closed interval, then it has to have a maximum and it has to have a minimum. So this doesn't tell us how to find the extreme values, it just tells us there has to be one. So most of our functions will fall into this category, that we can find a closed interval that is continuous on, and we will want to be able to find the maximum and the minimum values of the function. So this helps us to find the range of a function. You've had some FRQs that ask you for the range, so now suddenly by using a little calculus we'll be able to find out the range of a function quite easily once we know what the domain is. So let's talk about how do we find these. Extreme values, they're going to be very important for the next 6 or 7 weeks. How do we find extreme values? Well, we find extreme values by finding something that we call critical numbers, or you'll hear me more often call them a critical point. And C is a critical point if and only if, and this can be abbreviated as IFF, if and only if f is defined at the point, the derivative of f is 0, or the derivative does not exist. So this is another scenario where we've got 3 things that have to be true. The function is defined, the derivative is 0, or the derivative doesn't exist. There's 2 of these 3 have to be true. F has to be defined, and then either the derivative is 0 or the derivative doesn't exist. Then we call C a critical point. And you're going to find out that finding critical points is critical. That's something that you'll be doing quite a bit over the next 4 to 5 weeks. So finding critical points, they have to be where the derivative is 0 or the derivative doesn't exist. Now I'll go ahead and tell you a mistake that you're going to make is you're going to get in the habit of setting the derivative, of finding out where the derivative equals 0, but this part right down here is what you're going to forget to do. Where does the derivative not exist? That's one of those things that easily you forget about, so you need to make a note of that. Always look to see if the derivative does exist everywhere. Now, extreme values only occur at critical points or endpoints. Okay? So that's a critical thing to know as well. We're going to find the critical points, and we're going to find out the function values at the endpoints. So finding extreme values is really a 4-step process. And here's what it is. We find the critical points, we look at the function value at the critical points, and we look at the function value at the endpoints. And then we look at the numbers and decide which one's the smallest. The smallest value out, the smallest function value. Remember, we're trying to find out where the function is a maximum or minimum. So the smallest function value makes it a minimum. The largest function value makes it a maximum. So compared to what we've been doing, this is not a hard process always, but it's a concept that you need to be sure you understand. So let's look at an example. Find the extreme values, find the extrema of f on the interval -1 to 2. So the first thing we need to do is find the derivative. If we take the derivative of this, we get 12x cubed minus 12x squared. Second thing we need to do is we need to take the derivative and set it equal to 0. So I'm going to take 12x cubed minus 12x squared equals 0. I'm going to factor out 12x, and I get x squared minus 1 equals 0. So what values make this 0? We can get x equals 0 and x equals plus and minus 1. So these numbers that we just found right here, these are called our critical points. Let me see if I can write that a little bit better. And you should get in the habit of labeling these. I'm going to put CP here. That stands for these are our critical points. So we have 3 critical points. Now we're looking for the extreme values. We've got a closed interval. We know that because of the square brackets. So now we simply need to look at the function, not the derivative. We need to look at the function value at 0, the function value at 1, the function value at -1, and we cannot forget the endpoints. -1, which is one of our critical points, and 2. So we have 3 critical points and 2 endpoints we need to look at here. Notice that a critical point and endpoint can be the same thing. So we're going to look at this. What's the function value at 0? Again, remember we're plugging into the original function, 3 times 0 to the 4th minus 4 times 0 to the 3rd, and we get 0. If we plug in 1, we get 3 minus 4, which is negative 1. If we plug in negative 1, we get 3 minus negative 4, which makes it 7. And if we plug in 2, we get 3 times 2 to the 4th is 16, minus 4 times 2 cubed is 8. So we've got 48 minus 32, that's 16. And now we look, we've got 4 function values here to look at. Which one's the largest and which one's the smallest? The largest is 16. So we know then that we have a max at 2, 16. And we know that we have a min at 1, negative 1. So for this function, over this particular interval from negative 1 to 2, it reaches its highest point at 2, it's at its lowest point at 1. If we change the interval, will we do anything different? Of course we will. We'll have to look at different endpoints then, and also all of the critical points might not be in the interval then, but the process is the same. Another example. Here's our function. Find the extreme values over this interval. So we're going to find the derivative. F prime of x is 2 minus 3 times 2/3 x to the negative 1/3. Alright, that simplifies to 2 minus 2x to the negative 1/3. So there's our derivative. Now in order to find the critical points, we're going to set that equal to 0. 2 minus 2 over x to the negative 1/3 equals 0. How can we solve that? Well, if we take this 2 to the other side, we get negative 2 over x to the 1/3 equals negative 2. This should be a positive up here. We can cancel out our negative signs, and we get 2 over x to the 1/3 equals 2. Cross multiply, and we get 2 equals 2x to the 1/3. 1 equals x to the 1/3. How do we get rid of the 1/3 power? We can go in and we can cube both sides. If we cube this side, we get 1. Cube the other side, we get x. So we get x equals 1 out of here. So there's a critical point for us because the derivative equals 0. Now remember, a few moments ago I said we also have to look at where is the derivative undefined. Look right here at our derivative, either at this line or at this line. What can you tell me? Well, if I put 0 into the denominator right here, I get a 0 in the denominator. That won't work. So we have an additional critical point. We have x equals 1. We also have x equals 0 as a critical point. So we've got those two critical points we need to be concerned with. And that is what we would normally expect to get, is 1 or 2 critical points. But it's very easy to forget the 0 here because we don't get it algebraically. We have to look at where the derivative is undefined. So now we can simply look at the endpoint function values. We can look at the critical point function values. Oops, it's not 0, it's 1. And remember, this is the function values. We're not looking at the derivative, we're putting into the actual function here. So we get negative 2 minus negative 1 to the 2/3 power is negative 1. So we get negative 5 there. If we put 3 in, we get 6 minus 3 times 3 to the 2/3 power. Probably we'll need a calculator to figure that out. If we put 0 in, we get 0 out. And if we put 1 in, we get 2 minus 3, we get negative 1 out. So looking at these, well, we've got a -5. That's definitely smaller than everything here, I think. So this number right here, this will be our maximum value. Our maximum will occur at x equals -1. Our minimum, excuse me, I misspoke there. That's our minimum value, because that's -5. If you work out if you work out this number right here, I think you'll find that it's a positive number, and because it's a positive number, then it will be it would be your maximum value here. I do not have my calculator with me at this time. You can check it, but it's really simple. Once you've got these, your biggest one's your max, your smallest one's your min. You're smart enough to do that. It is possible to have multiple minimum or multiple maximum in a problem. If you get several points that have the same function value, and that is your highest or your lowest, then you could have multi-max or multi-min problems. Okay, we can do this with trig as well. So here, again, take the derivative, f prime. Derivative of sine is cosine. So we have 2 cosine x minus, we're taking the derivative of cosine, so it'll be sine, plus 2 sine 2x equals 0. Now, how do we solve this problem? Because we have the sine of x, cosine of x, and the sine of 2x. Notice that in the back I did use the chain rule to solve this problem. Well, you have to go back to your trig function, trig identities, and look up and see if there's something you can plug in for sine of 2x. And I think if you'll take just a moment, you can look and see that there is something you can plug in for sine of 2x. For the sine of 2x, you can put in 2 sine cosine x. So we can simplify this, or we can make this problem into this: 2 cosine x plus 4 sine x cosine x equals 0. Now that's changed to a 4 because the sine of 2x, if you look up on your trig identities, is 2 sine x cosine x times that 2 makes it a 4. Now we can factor. Some of you may think I can move this over and divide by 2 cosine x. And yes, you could do that, but you would be throwing away an answer in the process. So I'm going to factor a 2 cosine x out, and I'll have 1 plus 2 sine x left equals 0. So we set each one equal to 0. When is the cosine of x equal to 0? When is 1 plus 2 sine x equal to 0? You can use your hand trig for that. The cosine is equal to 0 at pi over 2 and at 3 pi over 2. And I get that from my hand trig. Notice that our interval is just 0 to 2 pi, so that's all we need to look at. And here we get the sine of x equals -1/2. Well, when is the sine 1/2? If you're looking at using your left hand trig, remember the sine is the right over 2, so that looks like it's at pi over 3. So we could say that the sine, we could say pi over 3, but remember pi over 3 is going to give us a positive 1/2 function value. We want negative. So where is the sine negative at? It's positive in the first and second. It's negative in the third and fourth quarters. Third and fourth quadrants. So we can use our rules to find it in the third and fourth quadrant. In the third quadrant, it's I believe our rule is pi plus the reference angle, and in the fourth quadrant is 2 pi minus the reference angle. And pi plus pi over 3 would give us 4 pi over 3 and then 5 pi over 3. So you see we've got 1, 2, 3, 4 critical points here. Do we need to worry about where the derivative is undefined? No, we don't have any fractions, so it's defined everywhere. So now to determine our maximum and minimum values, we simply look at the original function at 0 and 2 pi, because those are our endpoints, and at these 4 critical points, and we can determine what the max and min are. And I'll let you do that on your own there.